back over this later for whatever reason, I'll be able to link both the video we did earlier that did the first 2 pages and this one. And then I'll be able to have this, if I ever teach the class again, then that'll be the case. Okay. So, the next question, and by the way, part of this I didn't make up, because this picture of the crabs, that's actually real. There really is a set of crabs that have this pattern on their backs that look like a smiley face. Kind of a little distorted smiley face, but pretty interesting. Anyway, then the part that I did make up was, but then there's a mutant allele that causes you either to have a frowny face or a neutral face. Kind of like, so you can either be smiley, or you could be neutral, or you could be frowny, is what we're looking at there.
Seems that checks out. That's something nature would do.
Yeah. So just for fun. Okay. Now, so if you take a true breeding smiley crab and cross with a true breeding frowny crab, all the F1 display a neutral expression, and the F2 give these results. Okay. So what ratios have I ever given you that have 3 parts to them? 1 to 2 to 1. Okay. What else? 12 to 3 to 1. Very good. And 9 to what?
9 to 3 to 1.
Not 9 to 3 to 1. It's gonna add up to either it's gonna add up to either 4, or like the ratio parts are gonna add up to either 4 or 16. So 9 to 3 to 4. Okay. I think that's about all of them. I don't remember if there's any more, but I do know that the correct one is listed up there. Which one of those ratios matches our data the best?
9 to 3 to 4.
It matches a 9 to 3 to 4 the best. Now I've had a lot of students in the past try to say that matches a 1 to 2 to 1 ratio the best, but it really doesn't match it nearly as well as it matches a 9 to 4 to 3. And hint, the numbers I give you are going to match one of the ratios that we've talked about in class very well. It's going to be very close. When you do the chi-squared analysis, your chi-square number is going to be pretty small, which is going to give you a very, very large p, like a high p-value there, because I'm not trying to make it obscure or, like I want you, when you find the right ratio, it'll match so well that you should know. And it's not going to be perfect, but it's going to be darn near perfect. Okay? Great. So what pattern gives a 9 to 4 to 3 ratio? No. Recessive epistasis.
Oh, right. The additive is with the 4 different times.
Okay, so it's a recessive epistasis. Now, with recessive epistasis, we have, if you'll remember, there are the genotypic categories, which is A slash, or big A slash, big B slash, big A slash, little b, or little a, big B slash, and little a, little b. Okay? So you identify your 4 genotypic categories for recessive epistasis. And now how does it work in recessive epistasis? What do we group any of them together, or what? Because remember, of course, this is in the kind of Mendelian kind of way of thinking about it, this is the 9-part 3, 3, and 1, right? So how do we group them together to get a 9 to 4 to 3 pattern, or 9 to 3 to 4, whatever? So with hold on. You remember that most of those ratios in the two gene interactions, which this is, you can come up with the ratio by taking this 9, 3, 3, and 1 and grouping 2 or more of them together in a lump, right? Right. So what would you group? Which ones could you group together to take what is here a 9 to 3 to 3 to 1 pattern and group it instead and get a 9 to 3 to 4 pattern?
We take the 1 and add it into one of the other 3s.
So just for convenience sake, we could, because we've written it this way, we could group those two together at the bottom, and that's a 3 and a 1 part, and now you get a 9 to 3 to 4 ratio. So this 9 part, which part of the data does that explain? Which phenotype is represented then by the at least one dominant allele for both genes? The neutral one, right? The largest data category, right? If you look at the data up here, that's the largest category. So if you have at least one dominant allele for both genes, you get neutral. If you have dominant allele for this A gene, but homozygous recessive for B, you get what? That's the 3 part. So which part of that, which part of the data is that? That's the smiley, because remember, this is the 3 part. It's the smallest of the 3 up here. So this is the smiley. Okay. And
So you don't have to figure out which genes are
you just name it. You're making all this up. So you just name 2 genes, A and B, for all I care, and then figure out how they, like what genotypes of those 2 genes explain the phenotype. Does it make sense? Okay. So, and then what's the last category is the frowny, right? So what this says is if you're homozygous for little a, it doesn't matter what your genotype for anything else is, you're going to be frowny faced. Okay? All right, there you go. That's all that was needed there. Next part. Do a chi-square test to find out how confident you can be that you've selected the correct inheritance pattern. What is the chi-square value? Okay, so here we have neutral, we have smiley, and we have frowny. We have an observed, we have an expected, we'll have an observed minus expected, we'll have an observed minus expected quantity squared, and we'll have an observed minus expected quantity squared over expected for each. Okay? This is how we're going to set up our chi-square table. Well, we already have the observed numbers. Let's see, for since I did it in this order, neutral, that was the 170. For the smiley, that was the 3 part, that's the 57, and the frowny was the 74. For our expected, how would we find that?
add them all up, divide by 3.
Divide by 3?
Or, no, you'd want 16.
Yeah, it's right. You want 16 parts because what the 9, 3, and 4 represent really is that 9/16ths of the offspring should be neutral, 3/16ths should be smiley, and 4/16ths should be frowny. Oh, I have frowny. I have with an E there and not below, but yeah, you get the point. Okay, there we go. Just kind of scribble over that. All right. So, yeah, so right. So, first of all, we have to add all these up. Okay, we're going to clear that. Okay, so I want 170 plus 57 plus 74 equals 301. So we have 301 total. Now 301 divided by 16 is 18.81. I'm sorry. 25. Okay, that's equals 1/16 of the data. So now if we take that and multiply by 3, that gives us 56.4. So that's actually the expected for Smiley, isn't it?
Yeah, that's incredibly close to
So I told you these are going to be right on. And I like to hold on to as much information as I can for as long as I can. So while we've got that, number entered, why don't we go ahead and do the rest of the calculations for it, for that whole row at the same time. So we're going to subtract 57 from that. We get that number. The sign doesn't matter because we're about to square it anyway. It doesn't matter how I did that difference. Let's see. Here we go. X squared. Huh. Oh, okay. Is that right? No, that's not right. No, I just squared it again. Ugh. Okay, so 81 over 256. Clear. 81 divided by 256. Enter. Okay, that's the. Now we're at 0.314. So that's observed minus expected squared, right? Am I doing that right? Yeah. And now that divided by expected, which is that 56.4375, divided by 56.4375 equals a really, really small number. So I didn't write it down. I probably should have. So sorry, I should have written down the observed and observed minus expected, but since I didn't, I'm just going to go. Well, actually, I've got this one at least anyway. Oh, here it is. And then this one is 0.0056. That's probably as much information as we need. Okay, good. Good so far? All right, now I'm going to clear that. I'm going to go back to that 56.4375 because that was 3/16. Well, how can I take that number and make it 9/16? Just multiply by 3, right? See, so times 3 equals, now that's the 9/16 part, 169.31. How close is that to 170? 169. And the reason I do that is just because I don't want there to be any hesitation, any doubt that you've got the right number, that you get the right ratio. So I'm going to make yours pretty darn close. Not perfect, but within a couple of numbers of the exact right ratio. Not that we would ever really expect data to fit that good that often, but again, I'm trying to set you up for success and not confuse you about which ratio you have. So I wanted to make yours like pretty darn close to exactly one of those ratios that I've already taught you. 9:4:3, or 12:3:1, or 13:3, or 15:1, 9:3:3:1. In the two gene interactions. Okay, so we got 169. So we're going to subtract 170. Okay, so that gives 0.6875. I'm not worried about the sign because I'm just going to square it anyway. And it gives me that, in this strange way again, it gives me that 121 over 256. So if I, okay, 121 divided by 256 equals 0.47266. Let's just call it that. Okay, and then that divided by 170, 160, oops. Can I back up on this thing? Darn it, hold on.
Just use the little arrow keys and then you'll write over it.
Ah, very good. 69.3125. There we go. Equals 0.0028. These are going to be tiny, tiny numbers. Okay. And now the last one. Let's go back to 18.8125. That was our 1/16. And now I'm going to multiply that by something to get what should be 4/16. So what should I multiply 18 point whatever to get there? If 18.8125 is 1/16, then what would be my expected for the 4/16 part of it? Or what should I multiply 18.8125 by to come up with the value that should be my 4/16 or part of the ratio? By no. All right, what I'm saying is we took 301 and divided by 16. That gave us this number, which is 1/16 of the total number of crabs in this case. If 18.8125 represents 1/16 of the total, then how can I figure out what represents 4/16 of the total? Multiply by 4, right? Multiply that 18.8125 times 4 equals 75.25. Huh. How close is that to 74, right? 75.25. Well, I can tell you right now, the observed minus expected on that's 1.25. The observed minus expected, so let's just, you see how I did that, right? The difference between 74 and 75.25 is 1.25. Okay, so if we go 1.25, x squared is 1.5625. And if we do that, divided by 75.25 equals 0.0208, if I'm rounding there. Okay. Add all the, so now we're just going to add all these up. We get this 8 plus 6 plus 8 equals, what's that, 22? 2, that is 9. Okay, I get 0.0292. That is my chi-square value. All right, very good. Now I'm going to go take that 0.0292 and I'm going to go to the chi-square calculator that I showed you on, it's on Moodle. Linked from the lab page, right? We've already, you used, this is the same one you used to do your statistical analysis for your presentations you did today. Okay, from chi-square, I want, oh, I have to get back here to my keyboard. 0.0292. Wasn't that the right number? How many degrees of freedom do I have? 2, right? Because there were 3 sets of data. The frowny, the smiley, and the neutral face. So 3 sets of data, so 2 degrees of freedom. Compute P. And the p-value is 0.9855. You can't see that very well from where you are, but that's right here on the screen. It's very, very high. Your numbers are going to be high. Your p-value is going to be very high. Your chi-square value is going to be pretty low. Your p-value is going to be very high if you've done it right. So 0. Oh, by the way, and this says within what range of p-values? So just ignore that pit. Just give me the p. Just give me the p-value. Okay. The reason I did that is because what we used to do to find p-value, rather before we had the p-value calculator, is there's a p-value table in your book, and you would just like find where your number was between 2 other numbers and say it was within a certain range. That's hooey. It's baloney. Don't worry about that. I've shown you how to actually use the web, at least, to calculate the actual p-value. Okay, so 0.9855, wasn't it? Very good. Okay? So you see how to do that. All right. By the way, the meaning of p-value is that then we would expect that the data, that assuming that this recessive epistasis is the correct answer for what's going on there, and the only thing that's controlling the crab's faces, we would have expected that 98.55% of the time, the data we would have gotten from doing a cross like this would have generated results that fit the ratios worse than what we actually saw. Okay. All right. Let's see. All right. So, based on the pedigree below, is the allele that causes the genetic disease dominant or recessive? Well, what would be the hallmark of a recessive allele? Skip generations. What's the other hallmark of a recessive allele? I mean, so one way to say it is skip generations. Another way to say it is 2 parents that are phenotypically dominant or unaffected, in this case by your genetic disease or whatever, have a child that is affected, right? Same like, let's imagine that blue eyes is a disease, right? Both my parents were unaffected and I've got the disease, right? Ding, 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 ding. That's your clue. Anytime you see 2 parents that don't have it and have a child that does, that's bells and whistles saying ding, 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 ding. That's a recessive. It's inherited by a recessive allele. Do we see that here, though? We never see any instances of 2 unaffected parents having an affected child. As a matter of fact, anytime you have 2 unaffected parents, they don't have any affected children. And it doesn't skip generations. So what do we know about this gene or this allele? What do we strongly suspect about the allele that controls this character? Well, in order to be a carrier, that in that situation you have to have the allele that causes the trait has to be recessive. Because if the allele that causes the trait is dominant, then you won't have any carriers for that trait, because if you have even one allele for it, then you'll have the phenotype. Right? So we don't use the word carrier unless we're talking about a trait that is determined by a recessive allele. So since it doesn't skip generations, and since you don't ever see two unaffected parents having an affected child, as a matter of fact, every time you have unaffected parents, they only have unaffected children. That's a pretty good indication that the allele that causes this disease is dominant. Okay, so the not skip, skipping generations, that's a recessive thing. Having it come out of the blue from two parents that are unaffected have an affected child, that's a recessive thing, right? So, but since this is not what you see here, it's in every generation. That's most likely your dominant situation. All right, so first of all, we say it's dominant. Now, let's go and label everybody we can. Well, we don't know about him, but we know that he's probably heterozygous, but we don't really know. So this one here must be homozygous recessive, right? Because that's the only way for that person not to have the disease. This person here has one dominant allele. What else does that person have? Well, this one here is recessive. First of all, anybody that's an open square, we can go and label all of those in this case, little a, little a. What must this person be?
Must be heterozygous.
Why?
Otherwise, all of their children would have the
Exactly. If this person was homozygous dominant, then all of the children, this kid and that kid as well, would have the disease because that person would only have the dominant allele to pass on. So we can tell that this person's heterozygous. That way this kid can be homozygous recessive. Again, we could go and label all the open squares because we assume that this allele is dominant. We can label all the open squares as little a, little a. And the other thing is that since these kids that have the disease, but they had one homozygous recessive parent, so what must their genotype be?
heterozygous.
Right? They inherited their dominant allele from their dad here, but they must have inherited a recessive allele from mom, so they're also heterozygous. And in case we knew that for sure over here as well because this person is having unaffected children. But over here, we might have suspected, maybe this person's homozygous dominant, right? Because they're having all their kids are showing the dominant phenotype. That actually, if this was only information we had, if we just had this part, then we would say this person may be homozygous for that disease allele. But since that person had a mother that's homozygous recessive, there's no way for that person to have inherited a dominant allele from their mother, which they would have had to have been homozygous for it. So even though these kids just got bad luck, each one of them had a 50-50 chance of getting it, and they all did. Right? That happens.
That's a 1/8 chance.
That's going to happen 1 in every 8 times you have. Yeah.
Every 8 times there are 3 children.
All right. So that's how you answer that last question. Look at the pedigree. If it skips generations, or especially if you have 2 unaffected parents having an affected child, boom, that disease is caused by a recessive allele. If not, if it looks like this, it's caused by a dominant allele.
So if a parent produces a diseased child, but you don't know all their phenotypes except the one because they produced the diseased child, then you just put one of the alleles that you know for sure and leave the empty one because you don't know.
If they produced a diseased child, is the gene, do you think the gene that's controlling this is dominant or recessive? Sorry, do you think the allele that's controlling the disease is dominant or recessive? Recessive. So if the person is unaffected,
then
then they're at least heterozygous for the
Okay,
normal
gotcha.
allele, right?
Yeah. Okay. That
And
makes it
but since they're having an affected child,
easy. Mhm.
then they must be heterozygous for it, right? That makes sense? Because the only way for a person to inherit
Yeah.
the phenotype of a disease that's caused by a recessive allele is for that person to have gotten it from both parents. Well, unless we're talking about an X-linked situation, obviously that we know that. But I don't think I actually put that into play in any of these this X-linked stuff. That would be a good one to do, but I don't think I did.
Well, we just started learning.
Yeah, we
about
just
the
learned about it
X-linked
recently, yeah.
stuff, and this
It was,
is
though, in this
this
unit.
Oh, okay. I know we had just started learning about sex-linked traits, but
So the parents that give birth to the parents of the diseased child, so like 2 generations above.
2 generations back,
Are
yeah.
they going to be heterozygous too because they kind of pass down a disease, or?
So if you've got a grandkid, that's got the disease, one of their grandparents had to have it on the side of the Punnett square that we're showing.
Okay.
So if you can figure out sometimes you can figure out which grandparent that might be by looking at that grandparent's siblings, and if any of them have the disease, then that would indicate that that's the one that has it, right?
Okay, yeah. Figured it out then. That's good.
Yeah.
I'm gonna come in tomorrow. Well, I'm gonna just skip chapel because I have enough credit. So.
Okay.